Okay, so this is the second YouTube lecture for TBT 4165. I think I've corrected some of the technical problems that I had last time, so hopefully this time the cursor should be nice and visible and the screen should be glitching a little bit less. The topics for today will continue a little bit from what we're talking about the previous time and expand on the sort of modeling of gene activity we can do with FBA. So the first thing we're going to be talking about is we're going to be talking about how we can integrate gene expression data with FBA in something called the GXFBA, rather than just look at gene activity as a binary thing, but rather as a continuous thing as well, which is often the kind of data we'll have available. We'll also look at how we can do single and double gene deletion analysis using MoMA in addition to just FBA in its original form as we talked about earlier. And we'll see how when doing single and double gene deletion analysis in MoMA we have something called the Lazarus effect, which is quite contrary to many of the natural assumptions that we have in ordinary FBA, but can often be quite relevant for real-life cases. And after that, we'll finish off with a direct demonstration on how we can identify cases of the Lazarus effect in MATLAB. I believe that should be a pretty good exercise because identifying the Lazarus effect in an FBA model is, or in a metabolic model, is something that involves most of the relevant aspects of gene deletion analysis that we talked about so far. We're going to have to do both single and double gene deletion with both MoMA and FBA in order to identify this Lazarus effect. So to begin with, let's talk about GXFBA. So in its original format, FBA has a very binary view of gene activity. A gene is either on or it is off, and by that the related reactions based on the gene rules we have will also be strictly activated or disabled. But in real life, genes don't work necessarily in such a binary way. In real life, gene activity depends on expression, right? You have a process by which DNA is read off and is turned into mRNA, or is used to create mRNA, which in turn will lead to the expression of a protein. And that expression level is something that's a continuous variable. You can have, it's something that you can quantify, and they can have a variety of different values. And the higher the expression of a gene, the more there would be activity in their associated reactions. At least that is the thought. And so the question is, how can we integrate this kind of gene expression data into FBA in order to get a more accurate impression of the fluxes going on inside a cell? So first, in order to use GXFBA, we need to have two things really. First is, as in any FBA, a working genome scale model. We need to have an XML file or something similar that contains an overview of the metabolic capabilities of the cell in terms of reactions, metabolites, and so on, and of course the associated gene rules for the included reactions. In addition to this basic model, which is what we normally would just need to do normal FBA, we need to have gene expression data. And we're specifically going to need to have two gene expression data sets. One is what we're going to call the wild type. That is going to be our default conditions where either the cell is not subjected to any mutation, or where it's growing on something we can consider a reference medium in terms of nutrient availability. The second gene expression data set we're going to need is something that corresponds to a perturbation in our organism. Either we can have a mutant and we'll look at the gene expression of the remaining genes that haven't been mutated, or we might have some sort of environmental modification. The most natural would be something like a modified nutrient environment, but you could also want to investigate how the cell reacts to heat shock or some sort of toxic environment. That would also be a relevant case. So with these things, we want to fit our genome scale model so that, or the fluxes in our genome scale model, so that it fits the expression data as closely as possible. So how do we do that? Well, there's a couple of steps involved. The first is we perform ordinary FBA analysis on the base model. And from that we are going to get a set of fluxes, and that represent the flux distribution of our organism in its base configuration. Then we modify our model to represent the perturbed condition. For instance, that would be changing the nutrient environment in the model if that is the case. Or if we don't have anything that that corresponds to something that's directly modelable in FBA. For instance, if we're looking at heat shock, then that's really not something we could do in FBA directly. So then we'll just run FBA on the model in the same state, really, as for the wild type. But if we're doing if we want to look at a perturbed condition that corresponds to nutrient change or to a mutant, we would perform those modifications in our model. And so we perform FVA for that perturbed condition, and we will now get an upper and a lower bound for each flux in that perturbed condition. And we're not going to have any constraint on the biomass. We really just want to see for each reaction what is the absolute maximum flux that we can run through it. And from that we're going to find something that we call the characteristic perturbed flux, which is essentially the mean of the upper and lower bound for that reaction identified by FVA. After this, we identify those internal reactions for which we have gene data. That means not exchange reactions. And for all of these reactions, we want to set a new constraint. And that's going to be the constraint on a perturbed condition. Essentially, we want to restrict the flux in the perturbed condition to be the ratio of the expression values in the wild type in the perturbed condition relative to the wild type multiplied by the wild type flux. So for instance, if reaction 5, which is associated with gene 5, has a flux of 1 in the wild type, and the expression ratio of the perturbed condition relative to the wild type is 2, then we're going to set an upper bound on the gene expression on the flux in the perturbed environment to be twice the wild type flux. Since this gene would be upregulated, since it has a higher rate of expression than the wild type, we set this as an upper bound. If we have another reaction where the perturbed condition has the lower expression of the associated gene, for instance, a third, that the gene product, the mRNA of the perturbed condition has a third of the value of that of the wild type, we will set a lower bound for the perturbed condition corresponding to a third of the wild type flux. And from that, we will now have a bunch of additional constraints. From that basis, we now have a set of constraints in addition to all the stoichiometric and nutrient uptake constraints and so on that we had originally. And we want to formulate a new objective function, which is going to be as follows. It's going to be the sum of the log of the expression ratios between the perturbed condition and wild type, multiplied by the wild type flux, which is our variable. That is essentially what we're trying to optimize, or we're trying to find the values that optimize the Z for VI, divided by this characteristic perturbed flux. Which means that what this essentially does is that we are trying to force flux through those reactions that are upregulated by having a high value here. Since it's logarithmic, for anything that's upregulated, if C, then C is going to be over 1, which means that log of C is going to be over 0, and that's going to give a positive contribution to Z. So there we want to force fluxes through everything that is upregulated. Meanwhile, anything that is downregulated is going to have a C below 1, so this log of C is going to be negative, and so an increased flux through downregulated reactions is going to be bring down Z, which is undesirable. And so our optimization problem will then therefore try to minimize flux through downregulated reactions and maximize flux through upregulated reactions. If we want to do this visually, it looks a little bit like this. So here on the left is our pathway. Here on the top is our original wild-type condition, which is unperturbed. We have a classical solution space map where our feasible solution is here in dark yellow. Our direction for the original FBA problem, which is, for instance, biomass in usual conditions, is going to be in this direction. So we want to find the optimal solution for that, and that's going to be this point here. Then from this, we now have the overview of our wild-type behavior. And based on the gene expression data, we're going to now add a bunch of constraints. For instance, if we know that the reaction V5 here, that corresponds to our y-axis, has half or the associated genes for that reaction have half of the expression in the perturbed condition relative to the wild type. Well, then we're going to put a new bound here corresponding to that ratio, half of the wild type flux. And that's going to be, that's what we see here, right? Here we've added this constraint, which is new for the GXFBA problem. And this this is going to be the solution space for the perturbed condition. So we have a lower bound on reaction V5 based on the fact that the associated gene is downregulated by a factor of about a half. We might also have other constraints, for instance, on V2, but those constraints might be redundant. It might be a constraint that, say, would be lying somewhere around here, and so it's not really going to reshape our solution space. And now with this new solution space, well, we want to identify a new, or the direction of our new Z function. Because if we look at this optimization problem we have here to try to fit our fluxes through the expression data, this has nothing to do with growth. This is something that is going to push in the direction of increasing flux through upregulated reactions and decreasing flux through downregulated reactions. And so that is going to give us an entirely new objective function, which will correspond to a new vector. But this remains a linear problem. And because this V under here is something that isn't dependent on on the fluxes at any given time. This is something that will be constant for the model as a given, based on how we run the FVA for it. So this is strictly both this log2C mRNA and VI. These are a priori constants. The only thing that we can vary in our optimization is this VI. So it's a very straightforward linear programming problem. So that's going to correspond to a straight vector identifying the direction of optimal Z with parallel lines showing values of equal Z. And when we now have this new constrained solution and the new objective vector, it is simply a matter of doing an ordinary linear program. And in this case, this is going to push us towards this optimal solution here. You are going to have this week's computer lab exercise is going to show a little bit how you run GXFBA in practice. So I think it's one of those things that's more beneficial to actually try to get your hands dirty with. There's not too much more to say about it than this, really. So moving on, our next topic for today is what we call the Lazarus effect. And the Lazarus effect is quite unintuitive because in one way it's really directly contrary to the assumptions, or not even the assumptions, but to the rules that govern ordinary FBA. As I said in the last lecture, when you do gene deletions and you optimize by FBA, you are never going to have a higher growth by adding a mutation, right? So if you take whatever model you have, you perform a gene deletion on it, maybe it grows as fast with the deletion in case the gene is non-essential, or maybe it grows somewhat slower, or maybe it doesn't grow at all. But it's never going to grow faster simply by adding a mutation. Similarly, if you delete one gene, you find the growth for that single mutant, and you delete a second gene, that double mutant in FBA is never going to grow faster than any of the single mutants corresponding to those genes, either of the genes in that pair that we've mutated. But in MoMA, things become a bit different. Because what we can have in MoMA is we can have something like this. So we have, here on our y-axis is the growth rate, and we can imagine we're doing a mutation and we're following this over time with the number of generations here. And when we talked about MoMA a couple of weeks ago, we introduced it because it's more realistic in terms of depicting the behavior of a cell immediately after perturbation. FBA, the assumption of optimal growth, is quite valid given time because of selectionary pressure, but when you have an abrupt change either in your organism or in its environment, it is not necessarily going to perform ideally right away. It's rather, instead, it's going to likely enter a state that is as close as possible to what it was regulated to do before the perturbation came in, and then is going to gradually adapt to its new circumstances over time. So, for instance, if we do a single deletion here in red, what we can see is we can have a pretty abrupt drop in growth rate, and then over time it will evolve and then reach this green line here, which corresponds to the fitness of that single mutant. Now imagine we might have, for that single mutant, we can do various double mutations that will have the same fitness as the single mutant. That is quite plausible, right? Just as any single mutation may also not have any effect on the fitness, any secondary mutation might not have any additional detrimental effect on the fitness. This would be a case of buffering epistasis. Well, what we can often see is we can see that if we do a double mutation immediately, we're not going to do one mutation, adjust, and then do a second one. We're going to do a double mutation straight away. And what we're going to see is if we do MoMA on that double mutant, it's actually going to have a less abrupt drop in fitness than what the single mutant would have. It would have a less abrupt drop in fitness, and then similar as the single mutant, over time it will converge to the FBA optimal solution. The FBA optimal solution for a double mutant is not going to be higher than the FBA optimal solution for the single mutant, but for MoMA it might be the case, because in either case the MoMA solution is never going to be higher or correspond to higher growth than the FBA, because the FBA solution is the one that corresponds to the highest growth, while MoMA has an other priority than that, so it can sacrifice a certain extent of growth in order to satisfy its own objectives. But it's usually going to be somewhat lower. So how does this happen? Well, typically we can have something like this. So consider this is our wild type. Our lower pathway here is the most efficient way to convert our incoming flux into growth. And so that's going to be our optimal solution. Meanwhile, we can imagine that this transition from M2 to M3, or we can then think that this pathway M1, M3, M4 is corresponding to M1, M2, M4, but works slightly less efficiently. Meanwhile, we can also turn M2 into M3 and then into M4. But this reaction that turns M2 into M3 is hugely inefficient and will come at a great expense to growth. If we do FBA-based deletion, our best solution is going to be using this slightly less effective path that goes through just M1, M3, M4. and pass on. It's going to be somewhat less effective than going through M2, but not necessarily too much. And by FBA, we're going to find that one instantly. Meanwhile, if we run MoMA, MoMA doesn't care about efficiency. MoMA just wants to modify as little as possible. So instead of switching both this flux and this flux here will be knocked out because that is our constraint, so the MoMA problem has no choice, but this one can be maintained. And so MoMA will try to do that. And it will therefore try to do that, and instead of using this slightly less inefficient pathway, M1, M3, M4, and then out to growth with some loss, instead it's going to insist on keeping M1, M2, this reaction here, and then instead maintain mass balance and such by sending metabolite 2 over to M3 by this reaction, which has huge loss. And so this MoMA solution is going to be very suboptimal. Meanwhile, if we were to knock out both of these lower reactions, as we do here, now ideally MoMA would want to use this, but we're not letting it do this anymore. Its only choice now is to go through this upper pathway, which certainly is not as efficient as this lower pathway, which it could have used in the wild type, but is substantially more efficient than this middle pathway here. That goes from M2 to M3 with the associated loss here. We can look at this also otherwise in terms of the flux space. So imagine this is the wild type. We have our flux V1 and V2. We have our objective function Z, which coincidentally is strictly parallel with V1. And we have our constraints here. What we'll see here is that the optimal solution to this FBA problem when we optimize for Z is going to be this triangle here. If we now were to perform one mutation, which would correspond to adding a certain constraint, we will get that constraint could be represented by this dashed green line here. Now, if we're going to represent the immediate reaction of the cell to that mutation, what we're going to see is we're going to do that by a MoMA optimization from our wild type solution. And so what we want to do in finding MoMA is the point in this solution space described here by this area here, since we are restricted to the left of our dashed blue line here, below our original blue line and below our new green line, even though the original blue line is no longer relevant since this constraint here is strictly more constraining. We're going to be restricted in this area here. And what is the point in this area here that is the closest to our original surface? Well, it's going to be this triangle here, as shown by the fact that if we have this circle centered on our blue triangle, and we identify the point at which it touches our new restricted solution space, that is going to be here. Right? There is no point inside the solution space that is closer to the blue triangle than the green triangle, as shown by this circle. And of course, that is going to be since our solution space is much more restrictive, our Z is going to be correspondingly lower. If we were to leave this for a while and let it adjust to its new constraints, this green triangle here would be moving up the constraint lines and at the end converge on this point here. Suppose now that instead of doing the single mutant, we were to do a double mutant, which corresponds to adding both this green line and this red line. Now suddenly our double mutant solution space is quite constrained. It is only going to be this small area in here. And if we were to do this double mutant and we started the wild type, do the double mutant, well, we want to find the MoMA solution to that double mutant. What is the point of this surface that is the closest to our original solution? And that's going to be this red triangle, as indicated by the fact that it touches this red circle here that only touches our surface at this point. There is no other point inside the surface that also touches the circle, or is inside the circle for that matter. But we see also that this corresponds to an increase in Z, because we are higher up here. We're still a bit below, or quite substantially below, the wild-type optimal growth. But this specific mutation, secondary mutation, will actually have a faster growing MoMA solution than the single mutant that we find here. And that is a sort of flux space representation of how this this Lazarus effect works. That by adding constraints, since we are not optimizing for Z, but rather from distance to this original wild-type solution, adding constraints can actually have a positive effect on the associated Z for the optimal MoMA solution. So how does this look in real life? So for instance, here is, I think this is for E. coli, an example of the flux map. So this here, A, is the wild type, works at optimal efficiency. If we were to do a single deletion, we knock out this here, FBAA, which is the same as here, then it's going to follow into this regime by MoMA. And we're going to have this flux passing over here now. That is a characteristic for MoMA, but is quite inefficient. But it allows a minimal change relative to what the fluxes we have here. Meanwhile, if we were to try to do an FBA analysis of the single deletion, which would correspond to what this single mutant would evolve to do over time, we see that the fluxes here would follow something more like this. We're going to have a reversal of this flux here, which is a bigger change from our wild-type flux distribution than what we have in the MoMA distribution, but it's going to give us higher growth. Meanwhile, if instead of doing a single deletion on the wild-type, we did a double deletion where both this here and this here, and actually a triple deletion for that matter, where we delete this flux here, now suddenly our secondary deletion MoMA solution is going to be, this here is as close to flux distribution as we can get from this topology to this wild type. But it's also going to be quite a lot closer to the single knockout FBA solution than what the single knockout MoMA solution is to the FBA solution. So the characteristic approach to finding these Lazarus effect deletions is often, like, it depends of course on the model. Often it can be a bit more complicated than just one secondary deletion, but you will often see that if MoMA will force flux through a certain inefficient pathway, such as this one, while simply deleting that as well, and maybe some other secondary inefficient pathways that might emerge, that is going to force us into the optimal, the corresponding optimal solution. Often we can need quite a lot of mutants to have a full recovery. So for instance, here this is an E. coli minimal glucose. This is not the exact same model as the E. coli core model that is included in COBRA. This is a slightly more advanced model. And we'll see that, for instance, for NUO-A or for TPI-A, the single mutant is going to have a quite low growth rate off the bat. However, if you add a bunch of additional mutations in addition to that original mutation, you might recover something that is quite close to the original fitness, because what you're doing here is the cell is lazy. It wants to change as little as possible, and so it's going to maybe use some very inefficient pathways in order to be able to maintain fluxes through the other pathways it was using before. But if we delete those inefficient pathways that the cell is tempted to use, we force it into changing its ways in such a way that it actually reaches its full potential even with the deletion of this original pathways. And so yeah, that is like the basic primer on how the Lazarus effect works. Now we will move on to a little bit of an example on how we can identify such cases on a Cobra model in MATLAB. I think this should be beneficial because, as you will see, it involves both running single and double deletions individually as well, like as self-sustained or self-contained tasks. And so identifying these Lazarus genes is a good exercise that if you're able to do that, you're also able to do simpler things such as just original single deletions with both FBA and MoMA. Okay, so here's for the MATLAB demonstration on how to do a simple search for the Lazarus effect on the E. coli core model. So the first thing we do is, of course, we start up Cobra. In the Cobra toolbox, you might need to do this from your Cobra install folder, depending on how your MATLAB is set up. It loads all well, and so we start by reading in our model. Model equals read CB model. If you don't specify the file name, you're going to get this little prompt here. You find your file, your model file. Exactly where this is going to depend a little bit on your version of Cobra. And you have this E. coli core model. So it reads in this. If you have the correct model, these are going to be your parameters. And the first thing you can do is just finding the wild type flux distribution. So you can do wild type sol equals optimize CB model. Look at this. Okay, we find our growth rate and we have our flux distributions. Now this isn't super relevant directly to finding Lazarus effect, but it's always a nice thing to do just once you load your model. Make sure that it runs nicely, it's able to grow in its default condition, and it has, yeah, reasonable behavior. So then what we want to do is we want to run a single knockout analysis on our model. So we can start by then saying SNDel FBA. Let's use that name for our results, and we'll call the single gene deletion function on our model. So that is going to give us here a vector with the relative growth rate for each of our mutants. So we see that mutating gene 1, which corresponds to the gene B0008, is not going to have an effect on the optimal growth rate since the growth ratio is 1. Meanwhile, these mutants here, 2 through 4, they have a growth rate of slightly below 1, around 0.9. That corresponds to these genes here. So they will have slightly reduced growth, their mutants are capable of slightly reduced growth relative to the wild type, but nothing overly dramatic. Our next ones here, 5 through 10, will also be able to grow just as well with their mutant as the wild type. Meanwhile, we see that the mutant number 11, corresponding to the gene B0720, is not going to grow at all, even if we do an FBA type optimization. So now let's go for a MoMA optimization. So we can call it SNDel MoMA equals single gene deletion model, and now we pass it with the MoMA flag as well. If we don't pass, the secondary flag is going to default into FBA. And so this runs, and now we have our SNDel MoMA vector. And we see here, it's somewhat similar. We see that this first mutant here doesn't really have any different results from the single mutant, but we see that our mutants here, 2 through 4, will grow slightly less in if we do the MoMA approach. And we can see that, first of all, we can try to find SNDel FBA greater than 1. See if there's any FBA mutants that grow better than the wild type. And sure enough, we don't find anything. Now instead, let's try to see if there's any case where the MoMA single mutant grows better than SN del FBA. So we want to see if there's any case where the MoMA mutant grows better than the FBA mutant. Doesn't happen. And there's no case here either where we find that. But if we do it the other way around, see if there's any case where the FBA single mutant grows better than the MoMA mutant by just reversing the greater than operator here, we see that we get quite a few mutants where the MoMA mutant grows slower than the FBA, or the MoMA solution to the mutant grows slower than the FBA solution to the mutant, which is entirely as expected. So yeah, that is just a simple, quick run through of single deletions. Now let's do double deletions. Now, if I were to do a double deletion, I would do something like this: db del FBA equals double gene deletion model. This is going to take a little bit of time, so instead I've done as on a cooking show and just preloaded a variable. So I'm gonna just load this here, and it's going to give me this variable db del FBA, which is really the same as what I would get from running this double gene deletion model. It's just a bit faster doing this way. And we get a 2x2 or a 2-dimensional matrix, which shows the relative growth rate for each double mutant. So we see, for instance, this diagonal here really corresponds to just the single mutant, while this here would be a double mutant with both gene 1 and gene 2 knocked out, which corresponds to then gene B008 and B0114. Similarly, we see here that in the db del FBA relative to the SN del FBA, we can actually just look directly at this matrix, since we have the single mutants really on the diagonal. What you're going to find is that there is no element in this matrix, for instance on, say, row 14 here. The maximum value is going to be found at 14, 0.9318. Certainly some other double mutants grow just as well as the single mutant. That's a case of buffering epistasis. But there's not going to be any double mutant in the FBA solution that grows better than the single mutant. That is just not possible. How does this compare to a MoMA sort of approach? Well, let's have a look. Now, just as with single deletions and so on, we could do double del MoMA equals double gene deletion model MoMA. This would take even slightly longer than the double gene deletion with FBA, because MoMA, as it is a quadratic programming problem, runs somewhat slower than FBA. So we're not going to do that. Similarly, we've just pre-prepared our double del MoMA here, and this is what we get. It's the same format, right? We have a table with each point corresponding to a double mutant. So right, this case here is double mutant of 615, which is also the same as, or let's take 12, 12, 5. That's the same as 5, 12 here, right? 12, they're both 0.6574. The difference here is that it is no longer automatically so that our maximum elements are going to be on our diagonal. Now, of course, what you could do is you could just rummage around here, so to speak, and try to find somewhere like a row for which this isn't the case. This is a pretty minimalistic model, but even then, it's not that easy to just look around in bulk. So let's rather just have a script that does it. So we're going to have this for loop here. Now essentially what it does is, since we have 137 genes, right, we have our double del table is 137 multiplied by 137. We're going to loop through every row and then every column in every row. And we're going to see for each element in our double deletion, if the double deletion for MoMA corresponds or is higher than the growth rate for the single deletion corresponding to that row. And if it does, then we're going to write down the relative growth rate of the double deletion divided by the growth rate of the single deletion in this table that we'll call LAS. So let's just run this. There, runs pretty quickly. And we get this. So here we have mostly zeros. And the zeros correspond to fields where the double mutant either grows slower than the single mutant, even when looking at the MoMA for both, or where they grow just as fast. Then we're going to get 0 because of how our if statement is built. You know what? We have some cases here where it fills up, and that's where the double mutant grows faster than single mutants corresponding to it. And we see that for a lot of these, it's just 1.000, which often might reflect just a floating point error, and that the growth rates really are practically just the same. Or we have here where we have pretty marginal gains. And this is not particularly impressive, these values here. But what can we find if we look around here? Again, we can rummage around, see what we find. Here we see on the 21110 we have 1.25, which means that relative to the single mutant with gene 110 knocked out, the double mutant mutating or knocking out gene 2 on top of that is actually going to give a 25% higher growth immediately after the mutation relative to the MoMA growth from just the single mutant. What else do we have here? 1.4825, that's slightly higher. Here, 1.8019. What is actually the highest value we can find? Well, let's just do max of LAS. Let's call mLAS equals max of LAS. And we see that that's going to just give us the max for each row. So let's just do the max twice over. And we see that 1.8567 is the highest relative rate that we can find. So let's identify which double mutant that corresponds to. So first we can do find max LAS equals mLAS. Max LAS. I think this should be correct. And so you see that it returns 127. So if you look at LAS here, that corresponds to column 127. And oh yes, sure enough, we see here 1.8567. Those are the values that correspond. Let's see if there's anything else. So we can do find max or find LAS 127 equal mLAS. We'll see 107 through 114, which corresponds to what we have here. And what does that look like in terms of growth rates? Well, let's look at, so we can do then what is SN del MoMA of 107 to 114? 0.1059. Meanwhile, double del MoMA for these and 127, 0.1967. So we see that for each of these 7 mutants here, 8 mutants, 107 through 114, they have pretty dramatically reduced growth in their single mutant. Meanwhile, if you were to throw a second mutation on top of them, that second mutant is actually going to have a less detrimental effect immediately after the mutation happens. And this and it's only going to have 20% of growth instead of about 10% of the wild type growth. And yeah, that's an example of how we can identify these sort of like Lazarus interactions or Lazarus effect double knockouts in a model. I think we can leave it at that. I mean, you're welcome to try to play around with this a little bit more, but I think I've illustrated the concepts.